The broadcast is now starting. All attendees are in listen-only mode.
Hello, excuse me. Hello, I'm Cliff Tryans, Director of General Public Outreach for the National Groundwater Association. Welcome to the webinar, Groundwater Quality and Remediation of Emerging Contaminants. This is the third in a series of National Groundwater Association webinars for water leaders at the national and state levels. The first two webinars focused on groundwater sustainability and the groundwater food energy nexus. It is my privilege to introduce our presenters. John Horst is the Executive Director of Technical Knowledge and Innovation for North America at Arcadis. He is co-author of Remediation Engineering Design Concepts, 2nd edition, and an expert in the development, application, and optimization of new and innovative environmental restoration technologies. He will focus on the latest advances in characterization and treatment of constituents of emerging concern, drawing on related material he helped author in the regular groundwater monitoring and remediation column titled Advances in Remediation Solutions. Dr. Linda Hall, a Senior Associate Toxicologist with GSI Environmental Inc., holds a PhD in Ecological Toxicology and a master's degree in toxicology. She will address health hazards and regulatory responses to environmental contamination by substances commonly known as PFAS. PFAS have emerged as a widespread concern in drinking water with many sources and unique chemical properties that affect their fate and transport in the environment. During the presentations, feel free to type questions in the question box. At the end of the presentations, the presenters will answer your questions. Also at the end of the presentation, we will make a handout of their presentations available for downloading in the handout section. Without further delay, I'll turn it over to you, Linda.
Thank you, Cliff. All right, good afternoon, everyone. My presentation today focuses both on the health effects and on the regulation of a group of chemicals, a family of chemicals that we refer to as per and polyfluorinated alkyl substances, collectively known as PFASs. While these may seem like separate and unrelated topics, they actually are directly linked to one another in that virtually all of the regulations, advisories, and guidance that exist for PFASs in the United States today have been driven by concerns over potential health effects. Just to give you an idea of the sequence of information that I'll talk about today, I'm going to begin with some very brief comments, introductory information on what PFASs are to make sure that everyone has at least some common frame of reference here, talk a little bit about their production and use and how those uses have in fact led to their distribution in the environment, and discuss some of the key environmental sources of exposure in the United States, focusing on drinking water, move in to discussing toxicity, what we know, what we don't know, and then wrap up the discussion with an overview of PFAS regulations in the United States. So when we refer to PFAS, as I said, this is a very large family of perfluoroalkyl and polyfluoroalkyl substances. When we use the term perfluoroalkyl, it means a molecule where all of the hydrogens in that carbon backbone have been replaced by fluorine. And a couple of examples of perfluorinated substances are PFOA and PFOS that I show here in the upper left-hand corner of the slide. Polyfluoroalkyl substances have at least one hydrogen in that carbon backbone that has not been replaced by fluorine. So as those definitions suggest, PFASs tend to be highly fluorinated, and because of the strength of that carbon-fluorine bond, which is one of the strongest in nature, they tend to be persistent. And that persistence, in combination with their widespread and long-standing use, not only in the United States, but in Europe and throughout the world, has led to the fact that they are detectable and have in fact been detected in virtually all environmental media worldwide. And in addition to detections in environmental media, their presence has been measured in humans as well as in many species of terrestrial and aquatic vertebrates. So PFASs have and continue to be used in a really wide array of consumer and industrial products. Some of the list here, which addresses just PFOA and PFOS, will be familiar to you. Perhaps some of these uses less familiar. One of the ones that has great importance to this discussion and to the contamination of ground and drinking water here in the United States is a category of product known as firefighting foams, specifically the AFFF firefighting foams, which is a product category, again, that's going to come up over and over again in my discussion, especially within the context of drinking water contamination. So much of the toxicity, the regulatory interest, and academic analyses have, until relatively recently, focused predominantly on the two perfluoroalkyls, PFOA and PFOS, that I showed you the structures of in one of my introductory slides. PFOA and PFOS have been largely phased out of manufacturing in the US by virtue of a series of voluntary agreements between the manufacturers and the EPA. With those phase outs largely completed by 2015, PFOS was phased out first in 2002. Those phase outs have been supplemented by a series of significant new use rules under TSCA that limit the manufacture, use, and import of approximately 280 additional PFASs. These are PFOS, PFOA related. These tend to be what we refer to as precursors. That is, they're polyfluoroalkyl substances that can potentially degrade to the terminally stable PFOA and PFOS. So despite the significant new use rules that have been put in place, what we've seen is that there has in fact been a shift in manufacturing from the US following the phase out to overseas production of PFOA and PFOS. So they do in fact continue to enter the country, albeit at substantially lesser concentrations than when they were manufactured here. I'm going to skip down to the trends in use and mention that as far as trends in use of PFASs, I think I've indicated that there are estimates of hundreds to possibly several thousand of PFASs that are in use worldwide. The PFAS, PFOA, and PFOS that I've used as examples are also examples of what we refer to as long-chain PFASs. They have 7 or more fluorinated carbons. Those long-chain PFASs are being replaced by short-chain PFASs for the reason that short-chain PFASs are believed to be less toxic as well as less persistent than the long-chain PFASs. One of the issues there, however, is that the short-chain PFASs typically have not been the target of regulation here in the United States. There's one very notable and recent exception to that, but it also means, or happens to mean, that there is very little peer-reviewed toxicity data available on the short-chain PFASs. All right. So some of the environmental sources of exposure that have been important in driving regulation of PFASs in the United States are past industrial releases, ongoing use of consumer products. I've mentioned the overseas manufacture and import of various PFASs. I've also mentioned the importance of legacy AFFF firefighting foams. One thing I haven't previously discussed is wastewater treatment, effluent, and biosolids. And the issue there is that because of the strength of the carbon-fluorine bond, in most cases, when these PFASs enter a wastewater treatment system, they are not removed and are not degraded beyond the terminally stable compounds. And what that means is when that effluent is discharged to surface water, as is typically the case, the PFASs are discharged with it, and the same holds true for biosolids. So the presence of PFASs in these different products in the environment means that humans can in fact be exposed by ingestion of drinking water, ingestion of contaminated food, use of consumer products. And these exposures in the United States have in fact translated to detectable levels of PFASs in the blood of a significant portion of the US residents, and those are data that are tracked by the Centers for Disease Control and are available in the NHANES database. The highest levels of PFASs typically have been PFOS, PFOA, fluorohexane sulfonate, and fluorononoic acid, tongue twisters here. But importantly, the levels of PFOS and PFOA have declined measurably following the EPA phase out. So one of the most important sources of information that we have regarding PFASs in drinking water in the United States comes from an EPA program known as the Unregulated Contaminants Monitoring Rule. And perhaps, as suggested by its name, that it's a program that periodically identifies otherwise unregulated contaminants that have come to the attention of EPA because of concerns over prevalence, persistence, toxicity. And the EPA, following identification of a suite of new contaminants, heads up the sampling of public water supply systems that serve 10,000 or more customers, as well as sampling a subset of smaller systems. And in the most recent UCMR program, known as UCMR3, which took place over the period 2013 to 2015, public water supply systems in the United States were sampled for 6 different PFASs, and that sampling led to the recognition that between 1% and 2% of these large public water supply systems had detectable levels of PFASs. And what's interesting is even at that relatively low frequency of detection, upwards of 6 million residents were found to have drinking water supplies that were impacted by PFOS and or PFOA above the US EPA health advisories for those 2 PFASs of 70 parts per trillion. And another way of looking at these data is that 24 individual states had 1 or more public water supply systems with exceedances of that EPA health advisory. So in a study that was published last year, headed up by Cindy Hu at Harvard, a group of scientists analyzed the UCMR3 detection patterns of PFASs and statistically correlated the detections of those PFASs in drinking water with areas where AFFF firefighting foams had been used historically, not only to fight fires, but to train personnel in firefighting activities. And I've listed the sources that Dr. Hu and her group identified here: civilian airports, military fire training areas, AFFF certified airports, and also wastewater treatment plants, which often handle the effluent from these exercises. And so what the UCMR3 data and the subsequent analysis tells us is that historic AFFF use is in fact an important source of drinking water contamination in the United States, and I would say is perhaps the most important source that we know of at this point in time. And this drinking water contamination with PFAS has in fact been a driver for many of the advisories that have been developed by regulatory agencies. Switching gears and moving from drinking water to soil, the point of this slide is that over the 50 to 60 years that PFASs have been in commercial use throughout the world, that use has led to background contamination of soils worldwide, with the highest background concentrations in North America, in Europe, and in Asia. That's probably not surprising in that not only has manufacturing occurred in these regions, but they are areas where there's been very significant consumer use of PFAS-containing products as well. All right, moving on to a discussion of PFAS toxicity. Almost all of the peer-reviewed toxicology literature addresses a very specific subset of PFASs that are known as perfluoroalkyl acids. So we've got that fully fluorinated carbon backbone and a terminal carboxylic sulfonic or phosphoric acid functional group. In general, the toxicity of these PFAS increases with the number of fluorinated carbons, and I should say that the PFAS in commercial use typically have 4 to 14 fluorinated carbons. So the longer chain PFAS tend to be quite persistent. They're retained in blood for extended periods of time, which is why the CDC and the NHANES effort are able to detect them, to measure them in the US population. They're also characterized by having, in addition to their persistence, there is in fact a high degree of variability in the persistence of these compounds between species as well as within species. So if you look at the data I have here that contrasts mouse and human serum half-lives of PFAS, we're talking about days for mice, and yet a half-life of many years for the longer chain PFASs in humans. And also, these numbers are reflective, as I've said, of significant variability in those half-lives. PFOA and PFOS are by far the best studied of all of the PFAS. The majority of the toxicity data coming from animals, which is not surprising. That's generally how we evaluate the toxicology of environmental contaminants. We are fortunate, I guess one could say, in having a fairly robust epidemiologic literature, especially for PFOA. Insofar as their mechanism of toxicity, PFOA and PFOS are structurally similar to a group of naturally occurring compounds known as fatty acids. And what this appears to mean is that a number of the effects that have been tied to PFOA and PFOS appear to be related to the disposition, the aberrant disposition and use of fatty acids. There's a fairly broad spectrum of toxic endpoints that have been associated with PFOA and PFOS, again, primarily from animal data. Some of these are, in fact, linked to impairment of fatty acid disposition, including high cholesterol, liver disease. But in animals, there are also reproductive and developmental effects that have been observed. In humans, there's a fairly increasingly robust publication body of evidence for immune effects as well as other impacts as well. For PFOA, there was, as a consequence of one of the significant litigations that related to industrial releases of PFOA, something known as the C8 Science Panel was formed. That panel evaluated both animal and epidemiologic data and ended up concluding that there were, in fact, probable links of PFOA exposure and multiple diseases, including those I've listed here, most noteworthy testicular and kidney cancer, but also high cholesterol and a few other diseases. Importantly, though, that same panel found that there was not a probable link between PFOA exposure and 19 other discrete diseases that were studied. In the United States, the EPA has formally evaluated the carcinogenicity of only 3 PFASs, PFOA, PFOS, and perfluorobutane sulfonate. They concluded that there is, in fact, suggested evidence of carcinogenicity of PFOA and PFOS, not enough evidence to reach a conclusion about PFBS. Last year, the International Agency for Research on Cancer also evaluated the evidence for PFOA and concluded that there is limited evidence in humans for the carcinogenicity of PFOA based on the weight of evidence on testicular and kidney samples. Excuse me. So what do we know about PFASs other than these PFAAs? I've made the point a number of times now that there are many, many other PFASs out there in commercial use, and yet the majority of the toxicity data focuses on PFAAs. And what this means is that because many of the other PFASs are not well studied, if studied at all, it introduces a really significant source of uncertainty when we are faced with evaluating health effects of other PFASs. There simply is not much information that we can look to help us interpret environmental concentrations. Even for PFAAs themselves, for some of the less well-studied ones, there is some substantial uncertainty with respect to their toxicity, and that uncertainty has led to a trend to assess PFAA toxicity cumulatively. That's an approach that we've seen the US EPA take with the health advisories, treating concentrations of PFOA and PFOS either individually or collectively, but with that relevant target concentration, single concentration of 70 parts per trillion. Connecticut has followed suit, regulating 7 PFASs in that manner, and this is also a trend that we see being implemented overseas in Australia, Denmark, and Sweden in particular. So if I haven't explicitly made the point already, as I've gone through this talk and used the term regulation, it has really been in a very broad sense, in that the majority of current regulations are not promulgated legally enforceable standards, but are in fact advisory in nature. They are guidance. There are a few promulgated criteria, but they are definitely in the minority. So just a clarification that that is what I've meant as I've used that terminology, and it's what I mean as I'm going to go through these final slides of mine. So this graphic depicts current PFAS. Oh, I see this is one that actually didn't translate particularly well on PDF, but nonetheless, it's a graphic that depicts PFAS regulations in water, and by water I mean drinking water, groundwater, and surface water in the United States, with 11 states having either formally adopted or formally acknowledging the applicability of the EPA health advisory for PFOA or PFOS. This slide summarizes the current status of PFAS regulations in the United States. And what we've seen over the last 4 to 5 years has been a really rapid evolution or increase, I would say, in the regulation of PFASs, with a number of states in particular developing regulations for PFASs that go, first and foremost, go beyond just focusing on PFOA and PFOS, and also focusing on a number of environmental media above and beyond drinking water. So you can see by looking at PFOS and PFOA in particular that the emphasis has been on drinking water and groundwater, with 16 to 18 states adopting advisories, guidance, or criteria for those 2 chemicals. But 7 other states have drinking water, groundwater regulations for other PFASs, and there's this whole suite of other environmental media that have come into the focus of a number of regulatory agencies as well, including effluent, sediments, fish consumption, hazardous waste, New York and Vermont in particular. Consumer products, I've mentioned they are regulated in part by TSCA, but some of the individual states are also beginning to regulate PFAS in consumer products. And last year, the US FDA explicitly prohibited the use of 3 PFASs in food contact packaging materials. The point I wanted to make from this slide is to highlight that for PFOA alone, as an example, that there is a really wide range of drinking water concentrations that have been put forth as these are all advisories with the pending exception of New Jersey, which has proposed a maximum contaminant level for PFOA of 14 parts per trillion that has not yet been promulgated. But nonetheless, all of these concentrations are driven by a desire for the protection of human health. And they vary because toxicologists and other regulators that have worked to develop these advisories have differed in their identification of the critical studies, of the critical toxicity endpoint, what drinking water ingestion rates are appropriate, what the most sensitive population is, and they also differ in their assumptions with respect to what the relative importance of drinking water exposures are. That is, how much of one's exposure comes from drinking water versus other sources. And that term is shown here in the basis column as a RSC, the relative source contribution, with the US EPA assuming that 80% of your exposure comes from non-drinking water sources. And so that essentially leaves a relatively small amount that can be allocated to drinking water and still protect human health. Far fewer states have addressed PFASs in soil. Most of those, as you can see here, have focused on PFOA and PFAS alone. A handful are also looking at PFBS, PFBA. Texas stands out here in having soil criteria for 16 different PFASs. And I should also mention that the US EPA has regional screening levels that it has developed for PFBS and one of the PFBS salts. And with that, just about out of time, my summary comments are, as you can perhaps infer from what various points I've made in my slides, the regulation of PFAS is evolving really rapidly in the United States. They are also the subject of much regulation in Australia, in Europe. Most of the regulations to date are advisory. They're not promulgated enforceable standards. We've seen a number of select states beginning to regulate multiple PFASs, that is going beyond PFOA and PFAS. And these regulatory criteria, I gave you the example of PFOA. While they're health-based, there's a great deal of variability in them because of the supporting assumptions on what the critical toxicity and exposure magnitude is. With the overall regulatory trends being to treat PFAS in particular as having cumulative effects, and the focus in regulations moving beyond drinking water and groundwater. Great, thank you.
Okay, thank you, Linda. And I want to remind people before we move on to the next section of the presentation that you can type questions into the question box there. We're getting some questions, so as time allows, we will try to answer those. And also, about 15 minutes before the end of the presentation, we will put the handouts for of these presentations in your handout section. So with that, I will turn it over to John.
Thanks, Cliff. Good afternoon, everybody. So we're going to shift gears from Dr. Hall's talk a little bit and get into advances in characterization and treatment as it relates to emerging contaminants. And primarily we'll be focusing on PFAS to continue the trend in the discussion here, but we'll also touch a little bit on 1,4-dioxane. So maybe one question to consider before we jump right in is who decides what's emerging? Really, most groups keep tabs on the watch lists that the Department of Defense and the US EPA monitor. EPA, of course, has their unregulated contaminant monitoring rule where they're periodically sampling public water supplies looking for various contaminants, and the Department of Defense also maintains a watch list that they may monitor periodically at their facilities. In addition, there's public sensitivity. There may be something new that just pops up in the public domain that ends up garnering the attention of our various regulatory agencies, state, local, or federal. So this just gives a sense of where the information is coming from relative to what is emerging. The other I guess, kind of baseline concept to consider here, what are the pressure points? You know, in today's world, information is readily accessible, so visibility is a real issue. You've got regulatory drivers that are ever changing. You have reputational risk linked to that public sensitivity. There's uncertainty in the science and the lack of effective approaches in some cases for things that pop up on the emerging radar. And then there's vulnerabilities to consider. How do you prioritize how you respond? What are the risks? There's risks of reopeners, and then there's the consideration of making sure whatever you do, you're protected in the future, so future proofing. Some basic observations, however, as we head into this discussion about characterization and treatment. As Dr. Hall just discussed in her presentation, the standards and action levels are still evolving, and they're going to for some time for a great number of these emerging contaminants. Sometimes you have wide ranges. You saw in her presentation a pretty significant, more than an order of magnitude range just in PFAS compounds alone. And they tend to be trending down, not up. So that underlying toxicology is still evolving. That's largely responsible for those ranges and trends. How those studies are being interpreted and applied has an effect as well. When you start to look at characterization, there's no sensing tools like MIP or LIF, you know, the membrane interface or laser-induced fluorescence for characterization. And that's largely because sensing tools, direct sensing tools like that, are designed for concentrations that are much higher than the action levels that are being established for some of these new compounds. And then in addition, treatment can be challenging. You know, in part that's because of the low standards that have to be achieved, but in part it's because of the challenging nature of the chemical structures that we have to deal with. So we're going to touch briefly on characterization. And just to set the stage, you know, as an industry, our approach to site characterization for groundwater restoration, it's evolved significantly over the past 5 to 10 years. So we can be smarter about the overall scope and time frame of a characterization effort and the decisions that follow. So this graphic shows the different components of that have emerged over the last 5 to 10 years, the components of smart characterization, starting with an overall recognition that understanding the overlay of geology and mass is a really critical piece of characterization. And then from that realization, bringing the right tools to bear and the right resolution to really understand what's going on at the site. And then coupling that with real-time adaptive techniques that allow adaptive management during the investigation, not in many mobilizations, so that you can continually optimize what you're doing as part of your characterization and get to an endpoint much quicker, which also helps inform at the end of the day all of that, putting all of that together, informing better interpretation and decisions. So one thought to ponder when we think about any kind of emerging contaminant, in this case we'll use PFAS as an example, is how do you actually collect the samples? And what are some of the risks associated with that? Because at the end of the day, you're relying on the data that come out of those sampling efforts to guide your decision making. As we mentioned earlier, action levels are getting lower and lower, so the relevance of potential cross-contamination becomes greater and greater. This slide actually highlights some of these challenges as it relates to PFAS. You know, what kind of clothing do you wear? The kind of equipment that you use, the kind of decontamination procedures that you use, and how you check against cross-contamination in the field by using duplicates and matrix spikes and equipment blanks. So this is something that really needs to be thought through very carefully and taken seriously before you go out into the field to make sure that this doesn't become a fundamental stumbling block with respect to the representative nature of the data that you're collecting. So moving on from the sampling to analytical techniques, not all analytical techniques are created equal, especially when we're talking about new contaminants. This slide highlights a number of different analytical techniques that are currently available for PFAS compounds, and they all do something a little different. The two on the bottom, the time of flight mass spectrometry and the particle-induced gamma emissions, or PIGGY spectroscopy, those are not used widely, but they do have can serve a screening function. The ones at the top are more practical and used for forensics. So when you're trying to really understand what it is that you have at your site or at a site, these techniques can really help you get into that. They have much lower detection limits, and they can also help you understand the composition of the fluorinated mass that's there at the site. We're going to spend a little bit of time talking about the one at the very top, the total oxidizable precursor, or TOP assay. This is a technique that relies on oxidation of the sample to help transform precursors, which would normally be invisible to most of the conventional analyses, into the endpoint targets that the analyses actually detect. So what does that look like? This is an example of what that ends up looking like. You can see the sample as it was analyzed before running a TOP assay on the left. We have soil composite and a groundwater composite, both represented here. So the bar in each of those blocks on the left is prior to the TOP assay. And then the bar on the right shows what was detected after the TOP assay. So a pretty considerable change in mass that was detected before and after the analysis was run. So this is an example of how taking the time to do an assessment like this can really help you understand how much mass is actually present at a site that could become an issue in the future, because it's really these sort of end stage compounds that are most persistent. The precursors actually do break down in the environment to a certain point, and that's where they are able to be identified in the analysis. Is once you simulate that kind of natural degradation that occurs out in the environment, you can start to see what those precursors are producing. So it gives you a sense of what you might be encountering in the future and help avoid surprises. This analytical method is commercially available, mostly in the UK, Europe, and Australia. It's under development in the US. There are several outfits that are capable of doing it, and it's something that we've been working on for some time. And it should be commercially available here in the near future. So let's show a case study of what a characterization might look like. This is a case study of some characterization that was done at the Cape Canaveral Air Force Base. This was a high resolution PFAS characterization. So again, it follows that smart characterization mindset. The idea is mapping the geology, collecting groundwater in higher density sample points, so you get that higher resolution. This did use a fixed lab, so it was EPA method 537 to map PFOA, the octanoic acid, and PFAS, the sulfonate compounds specifically, and then did some incremental sampling in the sediments to understand the impacts there due to discharge. So this approach resulted in a much better understanding of what was going on at the site relative to these compounds. I'm going to skip ahead and just show what at the end point, what the results looked like in a three-dimensional rendering here. So this is the kind of detail that you can get when you do a high-resolution sampling event. One of the conclusions coming out of that study was that having a mobile lab that had the capability to run a PFAS analysis in the field would be incredibly useful to help drive investigations like this much faster and allow adaptive delineation in the field. So as a matter of fact, that capability is being developed and actually it has been developed. This is something that Cascade has set up. We partnered with them to help them set this up, and we just completed the first application of this mobile lab, and we're going to be publishing some of the data that came out of that. But this mobile lab setup has the modified EPA method 537 that is done in the field. It's DoD compliant. It's getting an ELAP accreditation, which should be obtained this fall. Can do both water or soil. 20 to 30 minute turnaround times. You're looking at about 20 to 30 samples per day throughput, depending on how efficient everything is. So, you know, this kind of setup can actually help save money over conventional sampling and fixed laboratory analysis when you're trying to characterize a large site. So this is something to keep in mind, as this is the direction that characterization overall as an industry is going, but it's being quickly adapted to be able to address some of these more difficult emerging contaminants. All right, now we'll talk a little bit about treatment. So generally, treatment is going to fall into, the individual techniques are going to fall into one of three categories: adsorption or separation, fixation, or destruction. And when we think about the treatment technologies that are out there and being considered for PFAS, we'll start with PFAS. You could argue this is a rendering that's, you know, our interpretation of where some of these technologies fall in a spectrum of that involves the range of practicability on the x-axis and the stage of development on the y-axis. So experimental to mature in terms of stage of development, and viability, not viable to viable in terms of the practicality. You can see there are some things that are both experimental and based on our assessment, not really viable, all the way up to things that are relatively mature and then kind of scrolling down, experimental but very feasible. So we're going to actually, as part of this discussion, focus on a few of those across that spectrum on the right-hand side of this chart. So activated carbon, ozofractionation, and polymer adsorbents. You can see the little red circle with the hash mark. Bioremediation and conventional chemox, at least as it stands today, are not viable technologies for PFAS compounds. So let's start with activated carbon. So granular activated carbon is currently the go-to solution for, in particular, PFOA and PFOS, PFOS. It's something that it can effectively remove those compounds from water, greater than 90% effectiveness. The contact times are relatively short. The media can be reactivated. So it's also something that can be useful for lower PFOA and PFOS concentrations and fairly low flow rates. So not only is it something that can work for surface water or groundwater, but it's also being applied in point of entry systems as a first line of defense. In terms of limitations, carbon's effectiveness decreases as the PFAS compound chain length decreases. So, and then there's the precursors as well that are not as effectively removed by activated carbon. So it's something that's something that's being looked at as again, the toxicology associated with this class of contaminants expands. There is competition for absorption sites with natural organic matter or other things that could be in the water beyond the targets. And it's something that requires a perpetual application until we get to the point where we have more aggressive technologies to deal with the larger issues. So right now, a lot of the focus associated with activated carbon is in the area of optimization. Activated carbon deployments, there's been many of these that we can point to. You can see here's a list of a number of fairly high-profile sites and incidents of PFAS and PFOA where activated carbon has been deployed either for larger scale treatment or in point of entry systems. So, again, GAC is typically the first line of defense, and it's often reviewed with respect to its applicability for the specific situation. So you can see there, we've ourselves have done greater than 50 bench and pilot scale studies related to the deployment of carbon to treat these kinds of compounds, in addition to the full scale applications that are shown on the left there. So shifting gears a little bit from the tried and true to something that's emerging, you have ozofractionation. This is a pretty interesting concept where the PFAS compounds are attracted to the air-water interface. So if you're creating bubbles, you can actually concentrate the PFAS compounds in the foam that you create, and then you can separate those out as a concentrate. So this technology really relies on that concept. It's using ozone to accomplish the bubbling. The ozone helps to separate concentrate the PFAS compounds. It also helps to oxidize some of the precursors. So it works through some of that mass that you can't see to make it more easily addressable. So the treatment process goes through a series of these columns, and then the water that comes out of the back end is then sent through an adsorbent for polishing, and the concentrate is shipped off for destruction. So this is a technology that we partnered with a company called Evocra to implement, and we do have a case study for a site where this was applied, and and applied fairly successfully, as you can see here. Worked extremely well for the PFAS and PFOA type compounds. And then it actually helped to convert some of the precursors to the compounds that we can actually deal with. So you see an increase in concentration, and then those compounds that were produced are then dealt with through the polishing step. This was, a small batch test, 3.6 million gallons of water. Total PFAS concentrations about 4 parts per million, just shy of 4 parts per million, and the targeted treatment for discharge is less than 1 part per billion. So something that's emerging and will continue to develop along with a number of other technologies, like this one, synthesized polymers. So this is one option, that for that polishing step that was identified. As a matter of fact, I think this is the material that we ended up using in that polishing step for that case study. So this is where you synthesize a polymer that can remove the contaminants and be regenerated many times. In this case, you have it's essentially a silica-based, organosilica-based absorption agent. It can be coated onto sand particles. There's actually a pure form of it as well. And the treatment potential with this is looking very good. And this is a company that we're partnered with, working with them to find different applications for this as we continue to develop the data and refine the application of this kind of technology. So that's it for PFAS. We thought we'd maybe touch on 1,4-dioxane briefly. 1,4-dioxane has obviously been around for a lot longer, so there's a lot more to look to in terms of treatment options. Air stripping and the use of activated carbon don't work for 1,4-dioxane. Advanced oxidation processes have been the go-to for 1,4-dioxane, but the interesting thing that's been occurring over the last 3 to 4 years is the realization that 1,4-dioxane does bioremediate, or it biodegrades and can be bioremediated. So that's where a lot of the focus has been more recently for 1,4-dioxane. So there's full-scale bioreactors that are being looked at for treatment as an alternative to advanced oxidation processes, and then also extreme SVE, where you basically desiccate source areas so that you can remove the dioxane and it doesn't stay trapped in the subsurface because of its affinity for water. So in closing, when you're responding to emerging contaminants, there's really 3 key things to consider in being prepared for these. The first is, your degree of proactive management and assessment of the risk and your readiness to deal with that. The investigation would be, considering how you're going to be smart regarding characterization and the analytical support. And then in treatment, really thinking about the immediate response versus future proofing. And, as the technologies develop, we're likely to see treatment trains becoming more important for individual contaminants. There is some light reading you could do here through the groundwater monitoring and remediation column, the advances in remediation solutions. There were 2 columns that were published in 2016 on emerging contaminants, and we'll be doing more of those in that series in the quarters to come. And some other reading that may be of interest as it relates to emerging contaminants. And with that, I think we're done and can take questions. Cliff.
Okay, thanks, John. We do have an audience question I'd like to ask. We have several. This question is, Have PFAS concentrations in humans decreased over the last 10 years? And if so, how much has it decreased?
In the United States, as I indicated, the Centers for Disease Control tracks concentrations of a suite of PFASs and has tracked those concentrations over time. What N. Haynes and the CDC has demonstrated is that PFOS and PFOA concentrations have dropped, and I would say they have dropped substantially between the last two N. Haynes monitoring efforts. We have, however, seen one PFAS increase in concentration between the two sampling events, and I honestly do not have the data in front of me, but I believe that it was PFHXS that has increased over time.
Okay, thank you. John, you mentioned treatment trains. We have a question. Treatment of PFAS seems to necessarily be evolving toward treatment trains. How do we minimize the challenge this presents?
Yeah, so it's funny. We had a session related to treatment in a recent workshop, and this question came up. The workshop actually included some water utility representatives, and that's something that's very much on their mind, as it is on anybody's mind who has to deal with these compounds, because treatment train can also translate to high cost. So I would say much of the innovation focus right now, there's two things. One, the initial response is to deal with the burning issues, right? So right now, the PFAS, FOS, and PFOA are the compounds that are, and a handful of others are the compounds that are being regulated. The activated carbon is dealing with those very well. So the industry is trying to stay ahead of the toxicology to look for things that can deal with the broader suite, and then really focus on simplification and scalability, recognizing that this is a challenge where if it's going to take multiple treatment steps, we want it to be something that's easy to do, and the infrastructure isn't necessarily costly to install or operate. So that's really where a lot of the focus is being applied right now.
Okay, thank you. Here's a question relating to regulation. Where do you see the regulation of PFAS heading over the next year or so?
Yeah, I think I see an increasing pace of regulation of PFASs in consumer products. I think that New Jersey is likely to go ahead and promulgate the first legally enforceable MCL for PFAS in the United States. I think that the trend that we're seeing is for the states to be taking the lead in the regulation of PFASs, and I don't think that is going to change. In other words, I think that that is going to continue. I also think that the example that we just saw in North Carolina for the state stepping in and developing an advisory level for a short chain PFAS is probably the first of many situations like that that we are going to see over the coming years.
Okay, thanks. Here's a long series of questions, actually, and we only have a couple of minutes, so I'll give it fast and you can answer fast. Given that there are so few guidance levels for PFAS, which ones should we be sampling for at contaminated sites? If we detect a PFAS, but there's no guidance or advisory, how do we interpret the sampling results within the context of human health concerns? So that's a mouthful. What can you say?
It's a mouthful, and it's really, really challenging. And in part, the answer depends on what the motivation is for sampling. So, for example, if you want to understand what PFASs you have, even if you can't fully interpret the health effects, then I would advocate to sample for as many PFASs as can be reliably measured, with the idea that at some point we will be developing additional toxicologic understanding that would support the eventual interpretation of at least some additional PFASs. You can alternatively sample for just a couple of PFAS, PFOA and PFOS in particular, if you're concerned as whether you're exceeding, for example, the EPA health advisory. And lastly, I would say another strategy to consider is that if you have the acceptance of your regulatory agency and their toxicologist, you can sample for a subset of PFASs that have regulatory criteria that have been developed either by different state agencies in the US, or you can look to Europe and Australia as well to increase your universe to perhaps 19 or more different PFASs. But again, you know, the acceptability of some of these alternate toxicologic levels really, you know, I would strongly advise consultations on the part of all stakeholders before one pursued that particular path.
All right. Well, that brings us to an hour, and I want to thank everyone, our presenters, most of all, for your excellent presentations, and the audience for being a part of this. You should have gotten a note, viewers, that the handouts are available for download, and in the next few days, I will be sending you an email with a link to the recorded webinar, which you can share with your colleagues. And with that, I'm going to bring it to a close, and I just want to thank everyone and have a great afternoon. Thank you.
Thank you.
Thank you.